Hashes are one of the most fundamental concepts in cryptography and blockchains. Cars have VINs, computers on the internet have IP addresses, and humans have fingerprints. These are all virtually unique identifiers for different types of objects. But what about data? Can arbitrary data also have a virtually unique fingerprint? The answer is yes, and they're called hashes. Let's dive right in. A hash algorithm is a function that converts any data into a string called a hash. Imagine a black box labeled SHA-256. The box has an input and an output. All we know about this box is that we can supply the input with any data. So we write "Hello World" on a piece of paper and input that into the SHA-256 box. The box consumes this input data and outputs a fixed length string of 256 bits. If we continue to input sheets of paper that say "Hello World," the output remains the same. If we change the input slightly, say we add a comma between "hello" and "world," the output looks completely different. It is still 256 bits in length, but looks nothing like the original output before adding the comma. You can think of that box as representing a hash algorithm, specifically SHA-256, and the box's output represents a hash. Well-built hash algorithms have two essential properties. They are pre-image resistant and provide collision resistance. Pre-image resistance means if a person will receive just a hash with no other information, it'd be almost impossible for them to reverse the hash algorithm and view the original data. They would have to brute force guess the original data from a nearly infinite set of inputs. Collision resistance means that finding two different inputs that result in the same output is essentially impossible. Again, we say essentially impossible because hash algorithms map a nearly infinite set of inputs to a finite set of outputs, meaning collisions will occur but be extremely statistically improbable. These two properties combined make hashes act as fingerprints or virtually unique identifiers of data. Hashes are used all over the internet, such as GitHub's use of identicons to give every new user a unique profile picture. Hashes are also utilized extensively within blockchains. When a new block is appended to a blockchain, it references a hash from the previous block, and the new block is then hashed itself. This process makes it so changing the history of the blockchain requires recalculating all of the blocks and all of their hashes. Don't worry if that sounded complicated. I'll explain this process in more detail in a future video. Hashes are also used within blockchains in data structures called Merkle trees to represent transaction data in a more compressed manner. Popular hash algorithms in blockchains include SHA-256 and Keccak-256. The 256 means that the hashes are always 256 bits in length. A great place to see hashes in action is Anders Browsworth's blockchain demo. You can find a link in the description below. You can see here the word "hi" and its resulting hash. If I add one letter to the end, let's say an M, the resulting hash is completely different. You can do this with any string. So let's type in Chainlink, and you can see that for each extra letter I typed, the hash always changed. Finally, if I type in "hi" again, I get the same hash as before. "Hi" will always result in this SHA-256 hash. This is a great demo, so make sure to come back here and check out how hashes work. You can think of hashes as the fingerprints of data, unique identifiers that are almost impossible to reverse engineer. Hash algorithms are a fundamental building block within blockchains, pun intended, and a solid understanding of their properties is essential for blockchain and smart contract developers. Now that you understand hashes, you're one important step closer to understanding what I mean when I say, I'll hash you in the next block.